Last episode, we scored login attempts for account takeover, and the whole lesson was that a false positive there locks a real user out of their own account. DLP is that same pain turned up to 11. Here, a false positive doesn't lock one login, it blocks a legitimate file transfer. The finance team can't send the board deck, the lawyer can't email the contract, and now your detector is the thing standing between people and their jobs. So DLP flips the optimization target. Most of this course has chased recall, catch the attack, DLP chases precision, never cry wolf. Let me show you why and exactly which threshold makes a block trustworthy. Here's the misconception this episode kills. A good detector maximizes recall, catch everything. That's the right instinct for malware and intrusions, where a miss is a breach. But a DLP block is an action against a real user. If 1 in 3 blocks is wrong, people stop trusting the system, file exceptions, and route around it. And a DLP control nobody trusts catches nothing. The number that kills this, at our default 0.5 threshold, the model catches more, but it also fires on benign transfers. Precision is what decides whether a block survives contact with a human. So, what does the model actually look at? Not the words in the document, content statistics. We engineer features. A regex and counter pass can compute on any outbound file, percentage of digits, whether an SSN pattern matches, whether a credit card pattern matches, keyword hits like confidential or salary, the document's character entropy, file size, whether the recipient is external, whether it's already encrypted, raw secret regex hit count, and an explicit confidential label, 10 cheap content derived signals, no NLP model, no embeddings. This data is imbalanced on purpose. Only about 10% of egress is genuinely sensitive. We saw in episode 3 that imbalance lets a model hide. But here's the twist. We are not going to crank skill pose weight to chase the rare class. For DLP, leaning the gradient toward catch everything is exactly backwards. We let the rare class stay rare and instead move the decision threshold because the operating point, not the loss weight, is where DLP's precision discipline lives. The honest scoreboard is the precision recall curve, the same idiom we used in episode 4 to debunk accuracy. PRAIOC here is 0.950. The model genuinely separates sensitive from benign. But PRAIOC is the area. DLP cares about 1 point on the curve. We walk the curve down from the top until precision first drops below 0.95, and we plant our flag right there. And here's the operating point that ships at precision 0.95, recall is 0.93, and the false positive rate is 0.5%. Read that as a promise to the user. 95 out of every 100 blocks are real sensitive data leaving the org, paid for by missing 7% of leaks at this gate. The misconception that you must catch everything dies here. We set a precision floor first, and the 93% we do catch produces blocks people obey. A DLP control that's trusted and 93% effective beats one that's distrusted and 99% effective on paper. Why accept the misses instead of fixing them with a heavier model? Because DLP almost never runs alone. The 14% this gate misses get a softer action, a second lower threshold that quarantines or warns instead of hard blocks and a human reviews. High precision buys you the right to auto-act, lower precision still earns a review. One model, 2 thresholds, 2 actions, and the precision 0.1095 line is the one wired to the automatic block. So the whole episode is one move. Train a normal model, then tune the threshold, not the loss, to the precision your action can tolerate. Autoblock needs 0.95. A slack nudge to the user might be fine at 0.80. The model is the same, the threshold is the policy. Now let's compute that curve and find the exact cutoff. Open 10 DLP egress.py. Top to bottom it builds the seeded egress dataset, trains XGBoost with no rebalancing, computes the PR curve, and walks it to find the precision 0.95 threshold. the one line of code that turns a score into a DLP policy. First, we synthesize the world, make classification with end samples 10,000, weights toast 9, 0.1, and random states 44 gives us 10% sensitive egress under a fixed seed. Then we rename the 10 columns to the real DLP features. PCT digits has SSN pattern, secret regex hits, and the rest. Same seed every run, same numbers every run. We split 75-25 stratified, so the test set keeps the 10% sensitive ratio. Then train a plain XGB classifier. Max depth 5, ETR 0.05, 400 rounds eval metric of CPR. Notice what's missing, no scale pose weight. We deliberately leave the gradient unbalanced because DLP fixes the rare class problem at the threshold, not in the loss. We score the test set with predict proba and compute average precision score. That's the 0.950 PR AUC, the area under the whole curve. Then precision recall curve hands back, the precision recall and threshold arrays, every possible operating point the model offers in one call. This is the heart of the episode. We mask the curve to points where precision 0.95, and among those pick the one with the highest recall, the most generous gate that still keeps its precision promise. That yields threshold about 0.34, where precision is 0.95, recall is 0.93, and we confirm the FPR is 0.5% straight from the confusion counts. We plot it. The full PR curve in red, a horizontal amber rule at precision 0.95, the budget line, and one marker where the curve crosses it, annotated recall 0.86. The printed headline, the marker on the figure, and the on-screen number are the same three values, one threshold, one promise. So DLP's secret is anticlimactic. Don't reweight rethreshold to the precision your action can afford. Next episode, we stop choosing operating points and start explaining them. A SOC analyst gets an alert from our episode 2 phishing model and needs to know why it fired. Episode 12, SHAP for triage, turning a score into a decision.